All right, so welcome to the first lab of the series, and we are into ping process deep dive lab. So let me go ahead and pull in some devices here. Let me pull up a switch and pull up a couple of laptops. Four is fine, and also have the connectivity done. Now, this particular software that I'm using is Cisco Packet Tracer, and pretty simple and straightforward to use. Most of the CCNA topology and commands work absolutely fine here with no errors. It's a free tool, but still I recommend strongly to not to install on your office computers. You can definitely do it on your home laptop, which I'm doing right now. Okay, so this is our four laptops connected to one switch. Let me go ahead and uh, assign some IPs. 1.1, the MAC address, I will keep it like A's, 4A. This one can be 1.2 and MAC address B, 1.3, MAC address C, and finally 1.4 and D. Okay, now once this is done, I will be assigning the IP in a static way to all the laptops. We do not have a DHCP in this topology. 1.1, and let me quickly do it for all the four devices. I will just change the last four characters of the MAC to make it look clean when we go into the uh, simulation mode. All right, almost done. The last one. All right, we are good to go. Now let me open the simulation mode, and there are a lot of protocols showing up here. I will just pick up the ones which I need. So for ping deep dive, we need to have only the protocols which we need to have: the ARP, of course, and the ICMP. And it's showing there on the bottom, ARP and ICMP. We're good. Now let me go ahead and go to the first 1.1 and try to ping 1.2, 1.1.1.2. Press enter and let us see what's going on. So the first thing first, you will see that the ICMP was the first packet, the ICMP request that got dropped, and then only we got the ARP request coming up. Now let's check out for the ICMP and see why that got dropped. Okay, let's open it up. In the ICMP, we see that the layer 2 information is blank. Okay, now switch being a L2 device, it will not understand the IP address. It's only got the layer 3 info like the source IP and the destination IP, and the switch cannot really figure out what to do with that, right? If I go into the outbound PDU, which basically means that the information which is traversing out of the device, you will see that here we are seeing the IP header. This is the big IP header, which we are going to discuss once we do routing. And this is ICMP, packet. And we do not have a Ethernet header here. Now that means that the switch really cannot understand what the ICMP packet wants or what to do with that source and the destination IP address. Now, few things here prior to I jump out into ARP request. Number one thing is the encapsulation and the decapsulation concept. Now in OSI model, encapsulation means that at the source, when you are adding headers from layer 7 to layer 1, that is called the encapsulation. And at the destination, when you are removing the headers from layer 1 to layer 7, then that's called decapsulation. And point number 2 is that just remember that all the lower layers will contain the information of the upper layer, which basically means that if it's the Ethernet header, that will contain the information of the IP. If it's an IP header, that will contain the information of the TCP and the UDP, like the port numbers and so on. If it's a TCP and the UDP header, that will contain the information of the services which are going to run between level 5 or the layer 5 to layer 7. Okay. Now, the point here is that when we are looking into this particular headers, we have got three headers here, three key ones. Number one is called the Ethernet header. Number two is called the IP header. And number three is called the TCP or the UDP header. Okay, from the CCNA standpoint, you really don't have to dive deep into the headers, but it's good to have a high level info, which I am going to share with you right away. So let's look into the ARP request. Now, ARP is the protocol that helps you to find out the destination MAC address. So let's see what it does. In the ARP, you will see we definitely have got the layer 2 info, and we are seeing that the ARP has got the packet structure like this. It's called the source MAC, then destination MAC, source IP, then destination IP, and the opcode. So source MAC is A, which is correct. Destination MAC is all F, which is a broadcast, right? Because we do not know the destination MAC yet. So ARP is trying to send it out through the switch to all the end devices connected to the switch. Source IP is the 1.1 and the destination IP is 1.2, which is all correct. Now let's have a look into the outbound PDU for the ARP. And there I'm going to show you some interesting stuff. So first of all, you look into the Ethernet header or the frame here that is showing up here, and below is the ARP, right? Now in the ARP, if you look, you have got the target MAC as 000. However, if you look at the top in the Ethernet frame, you will see the destination address or the destination MAC is all F. Now, did not we say that ARP is going to send out all the broadcast in Fs? Then why the ARP is showing here all zeros and the Ethernet frame is showing all Fs? The reason is that uh, Ethernet frame is a pure L2 frame, which means that there is no IP in information here at all. We all have got the source IP, which is all A's, and the destination, the source MAC, which is all A, and the destination MAC, which is all F's. That basically means that the Ethernet frame is actually doing the broadcasting. But in the Ethernet frame, we have got something called a type. Now this type is X0806. If it's X0806, that means it's ARP packet information. If it is X0800, that means it is about a IP version 4. Okay. Now X0806 means this entire frame is carrying an ARP with it. However, since the Ethernet frame is not having any IP info and it's a pure layer 2 protocol, the switch will look into it and say, okay, fine, the destination MAC address is all Fs. Let's do that. Let's send out all Fs to all the end user devices. There is one more point here, that is Ethernet frame is a layer 2 protocol, and ARP technically is a layer 2.5 protocol. So Ethernet frame lies on the bottom, and that will carry the upper layer information because ARP is 2.5, and that's why the ARP thing is showing up here, X0806. But if you go down to ARP, it says that it's all zeros in the target MAC. Now, the reason ARP is in 2.5 layer is because ARP lies in the boundary between your L3 and L2, and that's why ARP has got both the MAC information and the IP information as well. Now, looking at the ARP, we have got few things here. We have got the source MAC, which is A, all correct. The destination MAC, which is all 0, which is flagged by the Ethernet frame as all Fs. Source IP, of course, 1.1, and the target IP is 1.2, and the opcode. Opcode is 0x0001. Now, when it is 0x then 0001, that means the ARP is a request ARP. Okay, the response ARP will be in the form of 0x002. Now, why we need that? Because when the ARP packet will be broadcasted to all the devices, the device which is the correct one will pick it up and will know that, there's a request for me, and it will send out the response ARP packet in the form of opcode 0x0002. Okay. So now let's see what happens in the next step. ARP request going to the switch, and now from the switch, the request ARP will be broadcasted to laptop 1, 2, and 3. Here you go, all the three. And you will see out of all the three, the laptop 2 and the laptop 3 is going to discard the ARP. Why? Because when they open the packet, they see it's not meant for them. It is meant for 1.2 and they are 1.3 and 1.4. Okay, but 1.2 will accept the packet and say, it's for me, I'm 1.2, and it will immediately see, it's a opcode is 0001, which means a request. Now I have to send out a response to this guy saying that I'm 1.2 and my MAC address is BBBB, right? So this will again trigger the response ARP back. And while it does that, it will also update its own ARP table, which will be showing that the MAC address A belongs to 1.1. And once it will reach the switch will update its own MAC table, which shows the port number that goes to the laptop 1, right? Now, response packet of ARP, let's check how it looks like. Okay, we are here. And here you will see that in the response, we have got the source MAC as all Bs, which is great. And the destination MAC as all As. The source IP is 1.2 and the destination IP is 1.1, which is going back to laptop 0. Inbound means the information which is coming inside, and outbound means the information which is going outside, right? So this one, if you look into the inbound outbound, you will see that the opcode has changed now. It is 0x0002, which means it is a response ARP going back, and this response ARP has got the MAC address captured of the destination IP, right? Ethernet frame, now it is all clear. Your source MAC is all B, and your destination MAC is all A's. You are still in the 0806 because you're containing the ARP within you. And for the ARP, you have got the source IP, which is 1.2, the destination IP 1.1. Of course, your target MAC is the A and your source MAC is B. Now this B is captured into the ARP response packet. All right, all good. Now let's see the next step. This packet will be getting back to laptop 0. Once it goes back, immediately what will trigger is ICMP request, because ICMP request was discarded in the beginning, because it was not having the layer 2 information, or basically the destination MAC address. Now let's see what's going on there. If I go to ICMP request, yeah, now let's see. It says clearly that the ICMP is having the A to B. The source MAC address is A and the destination MAC address is B. And if you go to the outbound, it is having the Ethernet frame here. Now what has changed here? Of course, the source MAC address is A and the destination is B, but you will see that type also changed in the Ethernet frame. That is now X0800, not 61, which was the ARP one, right? 800 is basically meant for IPv4, because now this is containing the IPv4, I mean the IPv4 packet. So the type has changed. Now this has got two headers. Of course, number one is the IP header, which has got the source IP and the destination IP. They both are showing up here nicely. And if I go down, you will see the ICMP packet, which basically is the type. If you remember, the ICMP request type will be 8 and the response type will be 0. So all is showing absolutely correct here, and this is the ICMP request. Now let's see what happens with this. Um, Remember that in the entire flow, only the request ARP is broadcast, but all the other flows like your ICMP request, ARP response or ICMP response, they all are unicast. So let's go forward. Now the switch will directly push the ICMP request to the 1.2, which is happening now. And now this guy will be sending back the ICMP response. Let's go for the response. Yes, that's the response now. Let's have a check how it looks like. That's the response. And you will see it is going from source MAC address B to the destination MAC address A. Inbound, if I check, this is your 0800, which is IP version 4. Your destination is A and the source is B, which is all correct. That is your IP. And if you go to ICMP, the type has changed to 0. The type was 8, right? The type has changed to 0 because this is the ICMP reply. Okay. And this ICMP will be getting back to the laptop 0 or 1.1, and that's when the ping happens. So now let's check the ping window again, and you will see the responses came back. Reply from ICMP response packet 1.1.1.2. I mean, the ICMP packet size in Windows is 32 bytes. Okay, from 1.2, the packet size is 32 bytes. In Windows, it is 32, and when you are going to do it from a router, then it will be 100. Okay. Now, what is this TTL 128? Now, TTL 128 will remain the same when you are trying to reach a device within the same network, which means you have got, say, one switch and 20 devices connected. Then each of them, if you ping, it will always be showing 128. However, if you connect a router and if you want to reach to a separate network, okay, the number of hops you take or the number of routers you add, that is the number, the TTL number or the time to leave will decrement. So looking at the TTL number, you can always say that how many routers or how many hops you are away from your destination network. It's an easy way to find out. Let's say you have got one hop to go, then the TTL will be coming down to 127. Okay, so let me show it to you right now. And let's open up my command prompt and let's ping something. Ping www. Let's say google.com and enter, and you will see the TTL is coming down to 117, which basically means that you are 11 hops away from Google server. So 11 hops away means that 11 routers you have to pass through to reach the Google server. So that is 128. Okay. Again, the 128 value is for the Windows. If you're trying in Linux, it will be like 64 as default. If you're trying from the router, the default will be 255. Okay. So that's all from my end. I hope you enjoyed the lab on the ping deep dive. Thanks a lot for watching.